right, so section 2.2 is talking about histograms. So 2.2 histograms. So histograms are a visual representation of our frequency distributions that we talked about in the previous section. And what I want to do is teach you guys how to build these histograms. So if I pull out like an example from the previous section, like a particular frequency distribution, what we're going to do is we're going to create a histogram from this. So what we have is we have this data right here that I'm going to grab. Say average age of best actor of an Oscar, and there's their frequency. So we're going to use this to create that histogram. So what I'm going to do is I'll write down the histogram. So age, best actor, create histogram. So our table is going to have two different things. They're going to have age of best actor. I'm not going to write all the data in there for the Oscar, and then we're going to have their frequency. So what we have is we have 20 through 29. We have 30 through 39. So it looks like they're going by tens. 40 through 49. Remember that, again, the class width of this is 10 because it'd be 30 minus 20 or 39 minus 29. Or if you find the midpoints as well, which we're going to do in a minute here, you'll see that the difference between their, I should say their boundaries, the difference between their boundaries is also 10. Actually, the distance between their midpoints are also 10. So just evidence after evidence why that class width is 10. 70 through 79. Okay, and then our frequency goes 1, we have 28, we have 36, we have 15, we have 6, and then we have 1. So this is a frequency, not a cumulative frequency. So when we want to do our histogram is really, it looks a lot like a bar graph, but there's a difference between a histogram and a bar graph. Let's look at the definition first. So the definition says that a histogram is a graph consisting of bars of equal width drawn adjacent to each other. So adjacent means that these bars are right next to each other. It means that there's going to be no gaps. If there are gaps, that means that frequency happens to be 0 in that particular spot. So there are no gaps in a histogram unless you have 0 frequencies. The horizontal scale represents the classes of quantitative data, and the vertical scale represents their frequency. The heights of the bars correspond to the frequency values. So when we do our x-axis, they have some examples down here of types of frequency distributions. Like this is much more what we're going to be doing right now because we're going to do the actual frequency as opposed to the percent. So so here's this is what we're gonna build. You notice how these bars are adjacent to each other, that they're actually touching. And actually, if you look down here, you can see that the edges of these bars happen to be the boundaries of the classes. Now, you might not see that because you don't see the frequency, but when we build this, we're gonna use the boundaries to do this. And that's what I'm expecting you guys to do on a test. Is I want to see the boundaries. So when we create a histogram, what we're going to have is you're going to have vertical and you're going to have a horizontal axis. Now the horizontal axis is going to be, these are going to be the boundaries. These are going to be the boundaries of the classes. So when you look at these classes, remember the boundaries are the easiest ones are kind of to see in between like 29 and 30. What you do is you would average those numbers, you would average these numbers, you average these numbers, you'd average these numbers, and so on. You're going to find some boundaries. But remember, there's a boundary before 20, and there's a boundary right after 79. And I know it's easy to do in your head, but just to kind of verify like what they actually look like. So what you do is, if you want to find the boundary between 29 and 30, you just average the numbers. You take 29, you add 30, and then you divide that total by 2. Now make sure when you guys are doing these things, like if you want to do it all in one step, 29 plus 30, you have to put that in parentheses first, divide by 2. Because you need to divide the entire addition of 29 plus 30. So what I usually like to do is I like to go 29 plus 30, hit enter, divide by 2, and then hit enter. It's actually less keystrokes is why I like to do that. But you can see that you're going to get that 29.5. So we know there's also a boundary right below 20. So let's look at 20. We'll figure this out in a second. But the second one I know is going to be 29.5. You know, if you average 30 and 9 and 40, you're going to get 39.5. You're going to get 49.5 for, you know, between 49 and 50, and then 59.5, and you're going to have 69.5. You know, those are the boundaries between, you know, here and here, here and here, here and here, and so on. But remember that, you know, these classes are going to have a particular width. Like this class right here is going to be, you know, this bar that sits right here. You know, this is its upper edge. I'm also going to need to know its lower edge. So if you look at the pattern, you know that you can tell that these widths are 10, like we discussed before. Like these class widths are 10. So 10 below this is going to be 19.5. 10 above this is 79.5. So remember, this is the class boundaries of this. Now what we have to do is we have to create a vertical height that represents these frequencies. So what I look at is I look at the maximum number. I can see the maximum number is 36. So what I do is I pick a friendly number above 36. So like 40 would be the next friendly number. So usually I go by fives. So since 36 is above 35, I'm going to go to the next 5. So I'm going to go to 40. So let's see. 5, 10, 15, 20, 25, 30, 35, 40. So this is going to be 10, this is going to be 20, this is going to be 30, this is going to be 40, and you can tell the ones are 5s in between. So now I'm going to try my best to, you know, draw these ones, because remember, 1's pretty small. Like 1 would be this tiny number. So the very first frequency is 1, so it's going to have a height of 1. You know, it's going to be 1/5 of this, right? This is going to have 28, so it's going to go all the way up to 28, which is going to be here, but that's going to be the next box. Remember, these boxes are adjacent to each other. If I see any gaps, you're going to lose some points. That's why we use the boundaries, because the boundaries have no gaps. So that's 28. Next is going to be 36, should be about right here. So next is going to be 36. Next is going to be 15, which should be about right here. Next is going to be 6. And then 1. So that's how we create a frequency distribution. Sorry, that's how we create a histogram of a frequency distribution. Now, a lot of times we shade these things in. It's not necessary. Like, it's fine. Just do our best. So I'll ask you guys to do this on a test. I'll ask you guys to build a histogram for a frequency distribution. Again, the main thing that students tend to lose points on is they forget to use the boundaries here. They'll write these things there instead, and it makes no sense because then they have little gaps in their bars. Common types of distributions. So I'm going to show you some pictures, and we'll go back to this picture in a second here. So our types of distributions that we have is 4 different types that we're going to discuss mainly. We have a bell-shaped distribution, which is going to be a normal distribution. We're going to study this at length in chapter 5, 6, 7, and 8. So really we're going to be on this one a lot. A uniform distribution. You're going to have skewed right, and you're also going to have skewed left. So let's talk about, you guys are familiar with the bell-shaped distribution. A lot of people have heard of that before, so they call that a normal distribution. A uniform distribution, the reason why I call this uniform is because all the heights of these things are basically the same value. So say if I was going to, here, I'll give you another idea of a uniform distribution. Say if I was going to roll a 6-sided die, we might create a frequency distribution. So this would be, let's do it on a different page. If I had time, I'd actually just roll a 6-sided die about 100 times and show you that it's uniform. But what we could do is we could create the side that came out and then its frequency. Now what we know is these things are discrete numbers, so you can either get a 1, a 2, a 3, a 4, a 5, or 6 in a 6-sided die. Of course, the numbers like the 6. You're gonna get rid of those things. So, and then if I roll this thing over and over and over again, say if I roll this thing, I don't know, a bunch of times, like what you'll notice is that it's gonna look very random, but if you start keeping account of these things, you're gonna notice you're gonna get about the same amount of every single number. So, if you don't believe me, roll a die 100 times and keep count of all your numbers and notice how you basically will get about the same number. Now, remember when I always say about is because in in life, there's always a little bit of fluctuation. So, they're not going to be exactly the same number, but they'll be pretty close. What's kind of interesting is if you do this over and over and over and over and over again, that these numbers will become closer and closer and closer. So instead of doing 100 times, if you do it 1,000 times, the numbers will be even tighter. If you do it 100,000 times, they'll be really, really, really tight, and so on. So as that gets really, really large, this thing really starts to spit out that uniform distribution. So say I roll it a bunch of times. So this is like 8 of them. This will have 10. This maybe is 9. This will be 10 as well. This might be 7, and this might be 9. So what you can kind of tell, I know I put the 7 in here because I didn't roll it that many times essentially, so this is kind of, I don't making it up, but you could still get a kind of a low looking number, but it still is basically in the ballpark of the other ones. So if you create a frequency distribution, now I say they use the boundaries, so you're welcome to use the boundaries, but the book also sometimes does use the midpoint. So you could create back at this graph, you could have used the midpoints instead. So this x-axis, you could have had these things as midpoints, so then your bars would have looked like, well, that's too big. But your bars would have been here and then here. And so you could have used the midpoints as you want. And if you want to find the midpoint between 20 and 29, you just average 20 and 29. So 20 plus 29, enter, divided by 2. So you're going to see it's that 20 plus 29, enter, divided by 2. So then you're going to see it's that 24.5. So you could have used the boundaries as well, and that would have been okay. I mean, not the boundaries, but the midpoints. The reason why I bring that up is because these things are discrete numbers. So if you have discrete numbers, we usually just use the numbers themselves because essentially they are their own midpoint. But be careful when you guys build this frequency distribution. Do not put any gaps in the thing. So you can have 1, you can have 2, you can have 3, you can have 4, you can have 5, and you can have 6. Now I'm going to use the midpoints because these things are just discrete numbers. There's not a width in this class here other than 1. 6. So then, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, friendly number. So the first one is going to be 8 to here. That's not very good, whatever. The second one is going to be 10. Next one's going to be 9. Next one's going to be 10. This is messy. Next one's going to be 7. I shouldn't have put that 7 in there. It's kind of making it look off. And the next one's going to be 9. So the reason why I bring this as a uniform distribution, because they all basically have the same height. It's a very uniform height. They all have basically the same height is kind of the idea here. So that's what I mean by uniform. It comes from randomness, essentially. It comes from, actually, let's be a little more accurate. It comes from the fact that the probability of rolling a 1, or the probability of rolling a 2, or the probability of rolling a 3, and so on, is the exact same probability as each other. So the probability of rolling a 1 is a 1 out of 6. The probability of rolling a 2 is a 1 out of 6. Since the probabilities are equal, you're going to have this uniform distribution. But when you have a normal distribution, like the reason why something like this might come out is for instance, heights. Like if we're going to do average heights of women. I forget what the exact number is. Let me ask Google. Okay, Google. Average height of women.
5 feet 4 inches. According to Medical News Today, in the
All right,
U.S.,
that's enough,
the
Google.
average woman is around 5 feet 4 inches.
So the great Google told us that the average height of women are about 5 foot 4 inches. So what we were kind of expecting because of average, what we know is that this main bar is going to be about 5'4" would be this number right here. Now you're going to have someone that are maybe 5'5" and 5'6" and 5'7" and 5'8" and 5'9" and 5'10" and so on. You're going to have very tall women. You're also going to have very short women. But more often than not, most women are going to be around that 5'4" range. Now remember fluctuation, so probably from like 5'2" all the way up to 5'4". It'd probably be like 5'0" all the way up to 5'6" would be a lot of these numbers right here. Now, as you get really, really, really tall and really, really, really short, there's going to be less women that are those particular heights. So that's why you get very small frequencies. So really, this represents a frequency distribution. Most of the frequencies are going to be around the average, and then the lower frequencies are going to be around the very short and the very tall. Now, a skewed right. Now, most people don't think that this looks skewed right. Now, what skewed right means is look at the tail. Do you notice how this tail kind of comes off? And and this is skewed left. Now this is kind of a cool picture to help you remember. If you look at your foot, do you notice that this kind of has that shape? Now this is your left foot, so your left foot is skewed left because the tail kind of goes left. You notice how it kind of goes left? That's why it's skewed left. and this is your right foot, notice how it's skewed right, because the tail goes off into the right. So that's why this one is skewed right, because it's talking about this extended tail, and this is skewed left because it's talking about this extended tail. You know, they're bell-shaped, but they're not symmetric. So that's what makes a normal distribution different than a skewed, that this is bell-shaped, but it's symmetric. And those are the things that they're asking you guys about. Oh, let's do some examples real fast. Something that's skewed right. Actually, something that's like highly skewed right might be income. So what we know is that most people are going to make about a certain amount of money. Like, ignore these x-axis. I'm just like saying this might be around 50, 60, 70, 80,000. I don't know what the average is anymore, but the median is. So, you know, most people are going to make about this amount of money. And then, you know, you're going to have some people that are less. But what you're going to have is you're going to have some people that just make a ridiculous amount of money. Now, wealth is extremely skewed right. Like as far as the skewedness, this goes off the page and through my wall and all the way into the river. So that's kind of how skewed right it is, because, you know, we have people that are making like say $80,000, but you have people that are making billions of dollars. So, you know, they're so far skewed right that it's off the, you know, it's almost off the planet. But that's an idea of for skewed right. Now, something skewed left might be like death, for instance. Like, most people are going to die or at the average age of death, but, you know, you're going to have some people die when they're very young. And, you know, it's going to kind of, you know, most of them are going to be here, but, you know, you can have deaths when you're young. And then when most people pass away here, there's going to be a lot less people that you know, get to be 100 years old. So this actually might be age. This thing might exactly be age. Actually, that's exactly what it is. Okay, so as far as what I mean by that, by its axis.